Hey there, I'm Aditya Bacharne and we are going to make this project, Serial Dynamic Memory Allocation. Um, I saw this project got recommended to someone on a Reddit under the Reddit post. So also let's talk about my motivation to make this project. So first of all, it was like cool to read about this. Like I've read like the first part, like what I have to make and all, but I'll be rereading it. Yesterday I tried to stream this introduction video, but like my internet speed sucks. Uh, so I'm just going to record this and I'm going to upload it. So serial dynamic memory allocation. Okay. Okay, I'll. So I tried to uh, record a further part, but the recording, I messed up somewhere. So let's just do it again. No problem. So in this project, you will implement a fast and space-efficient single-core memory allocator that follows the semantics of libc's memory allocator. So this is where I read libc's memory allocator functions. I didn't know what they are, so I googled that. Also, since you have read this, uh, the title of the video, yeah, or here above. The title of the video is going to be not going to be. Okay, the title of the video is like no clankers. By clanker, I mean no ChatGPT, no Claude, no DeepSeek, no Gemini, no LLM. Even for even for understanding some stuff, learning some stuff, and writing the code part. I'm not going to use it at all. No clankers in my stream. Technically, it's not a stream, but no clankers in this project. No clanker ain't gonna touch my my land. This is my private property. I don't know why I did that accent. I think I'll cut it out. I think I will not. I'm a lazy bunch. Okay. So let's talk about libc's memory allocator functions. So I googled what is libc's memory allocator function. I just pasted in here along with the full stop. So I first tried this link. Yeah, I first tried this link. I just regret clicking on that. It's too confusing. If you want to take a look, this is what it looks like. See, I clicked on this. Oof, the knowledge. Yeah, we're just going to quit that. Okay, so this person asked this, pause your video, read this, and I was like, I reached till here. So R limit as, I'm not sure what it means, but I'll just keep reading. I'll figure it out maybe, or it's like too deep for me to go into that rabbit hole. Uh, where was I? Stacks usually consume several megabytes, which means you can create only few hundred threads because you have no more free address space. Maybe an even more common reason for exhausted address space are memory leaks. libc of course tries to reuse space on heap, space obtained by brk syscall, and tries to mun m mu mun mmap unneeded mappings. Oh, it's unneeded mappings. Mm, no, okay. However, it can't reuse something that is not deallocated. Okay. I think it's mostly talking about the deallocation stuff. Okay, I think I'll cover the libc memory management in this PDF. So this is the Linux programming interface. Okay, first of all, if the creator of this book is watching this, I will buy it eventually. I will buy your book eventually, but just don't sue me. So this is the part, memory allocation. I'll be reading this. So from this, you can see the BRK and SBRK are mentioned over here. I'll be reading this, but not in this video. In this video, I'll mostly just complete read the entire PDF, the project description, and That's it. In the next video, I'll be reading memory allocation or something else if I have to. But yeah, this is not for today. Also, I'll stop this. Oh yeah, I have to like look up quick. What is map? Ellipse memory management. I think it. Oh, clanker detected. Clanker detected. Clanker. Okay, I am not going to lie. Okay. Okay, text segment, virtual address space, partitioning, text segment. Okay. Yeah, virtual memory mapping. Virtual memory mapping allows files or device contents to be mapped onto a processor's virtual address space, commonly used for dynamic library loading and file or I/O optimization. Linux implements this via mmap. Okay. Okay. The virtual memory layout of the process. ठीक है. Okay. I understood everything. Yeah. Okay. Deliverables, it's not nothing. Okay. Getting started. Let's go. So Snail Speed Limited makes liberal use of dynamic storage allocation through the use of malloc. You would like to speed up as much of Snail Speed's code as possible, but it is not feasible for you to rewrite their entire code base. In an effort to maximize the value of your work, you decide to write an optimized storage allocator, which may be used to improve the performance of a large number of snail speed applications. Okay, so I have to I cannot make changes to their entire code base, like the snail speed limited's code base. So I'm just going to improve the uh, memory, the storage allocator. I'm just going to optimize the storage allocator. You have generated a number of memory allocation traces from some snail speed applications. Since these traces are representative of the sort of work that the dynamic storage allocator will be asked to do, you should make sure that your allocator performs well on these traces. Okay, so I am assuming, so that the sentence that I've read here, I'm just assuming what it means. So by traces, I think they mean these are all the functions, or these are all the things that the process asks asks us to do, and like we have to improve we have to see a better performance on those kind of tasks. So I think that's what the traces mean. So snail speed applications are often run in memory scarce environments, and so a good solution should be fast and have as little memory overhead as possible. Okay, got it. Snail speed has serial programs which use dynamic memory allocation. Okay, had serial programs which use dynamic memory allocation. Okay. By serial, do they mean like single threaded? What does it mean? Yeah, it's in the title too, serial dynamic memory allocation. I'm not sure, I think it's single threaded. Your goal is to build a fast, space efficient, general purpose, single core memory allocator. You will also build a test suite to ensure that your allocator is functionally correct. You should use the techniques discussed in class to balance free list maintenance time with memory overhead. You're also encouraged to try out auto tuning, don't know what it is, which allows you to programmatically find optimal values for parameters that control the allocator's execution. Okay. 2.1 team formation. Yeah, okay, team code, getting the code. Getting the code. Remember that we expect groups to be practicing pair programming. Okay, not that important. I think it was. No, not important. Okay. Yeah, not very important. Heap memory allocator interface. Your dynamic storage allocator will consist of the following four functions. Okay, it has four functions, which among those functions are declared in allocator interface.h and defined in allocator.c. The allocator.c file has given you the allocator.c file we have given you implements the simplest functionality called malloc. Functionality sorry, I'm so sorry. The allocator.c file we have given you implements the simplest functionally correct malloc package that we could think of. Using this as a starting place, modify these functions and possibly define other private static functions so that they obey the proper semantics. Okay, so int my initialize void before calling my malloc. Oh, I have heard the name my malloc. I think low level has made a video on this. I'm I haven't watched it. I just like googled, like I was just looking for like what uh, like if people search. So I'm trying to hide this channel from my friends, so I haven't told them, but I just told them I'm going to make this project on dynamic memory allocator. So I'm just looking like if my channel shows up or not, if we type dynamic memory allocator. I think I saw low levels video on this. Yeah, let's just search. Yeah, my luck. Oh, that's see to prove a point. I think it's not same.
Malloc sucks. So I spent the
I think I shouldn't say it. Yeah, I think it's different. Yeah. So I guess it's sort of it was a different thing. Before calling my malloc, my realloc, or my free, the application program that is the trace driven driver program that you will use to evaluate your implementation calls my init. Okay. You may use this function to perform any necessary initialization such as allocating the initial heap area. The return value should be -1 if there was a problem in performing the initialization and 0 if everything went smoothly. Okay, so we are going to write this function which is myInitialize. It will like initialize some stuff that we want to do. Also, it will allocate the initial heap area. Got it. Uh, Void myalloc size t size. This call, I don't think I should read this. Like okay. Uh, this call must return a pointer to a contiguous block of newly allocated memory. Uh, sorry. This call must return a pointer to a contiguous block of memory, a block of newly allocated memory, which is at least size bytes long. Okay, so we call my malloc function with a parameter of size, and we have to return a pointer to the like beginning of the block. The entire block must lie within the heap region and must not overlap any other currently allocated chunk. The pointers returned by my malloc must always be aligned to 8-byte boundaries. Okay, the pointers returned by my malloc. Okay, first of all, let's read this again. This entire block must lie within the heap region and must not overlap any other currently allocated chunk. Fair. The pointers returned by my malloc must always be aligned to 8-byte boundaries. You will notice that the libc implementation of malloc does the same. If the requested size is 0 or any error occurs and the requested block cannot be allocated, a null pointer must be returned. Sure. How about I think I should just Google it. Okay, so I'm not sure what they mean by 8-bit boundaries over here, so I'm just going to Google it. 8-byte boundaries in malloc. What does 8-byte alignment mean? Is this the same stuff? Okay, I'll just read this one. Clanker. In libc's malloc, the function is said to return a pointer to a memory region of at least x bytes. Okay, in libc's malloc, the function is said to return a pointer to a memory region of at least x bytes, and the pointer is aligned to 8 bytes. What does this alignment mean? Thank you. Okay, so it means that the pointed address mod 8 is 0. Okay, got it. So it's a multiple of 8. This can be important for low level operations where it may impact correctness or efficiency. It means that the memory starts on an address that is multiple of 8. Oh, it doesn't basically mean like the memory allocated is like a multiple of 8. It means that the address starts like the starting of the address is a multiple of 8. Okay, as for why you would even care for memory that's not aligned, sorry, the CPU sometimes requires two accesses to read it all. In some cases, it won't even try and just throw an error. The mention of, I'm not sure what that means. Uh, the mention of aligned to 8 bytes is that the caller knows whether it will have to do any fudging of the pointer or not. Usually you won't care. The compiler takes care of most of the alignment issues, but the info's there in case you need it for some reason. The addresses are a multiple of 8. Okay. Okay, so let's read this again. So like it will click in. The call must return a pointer to a contiguous block of newly allocated memory, which is at least 6 bytes long. Fair. This entire block must lie within the heap region and must not overlap any other currently allocated chunk. Fair. So it's no, it should lie within the heap region that we have allocated in the myInitialize function. Sorry, and it should not overlap with any other function. Like it should not overlap with any other process. The pointers returned by mymalloc must always be aligned to 8-byte boundaries. Okay. You will notice that the libc implementation of malloc does the same. If the requested size is 0 or an error occurs and the requested block cannot be allocated, a null pointer must be returned. Got it. So void my free pointer. This call notifies your storage allocator that a currently allocated block of memory should be deallocated. The argument must be a pointer previously returned by mymalloc or myrealloc and not previously freed. You are and not previously freed. Yeah. So what this function does, we have to like give the input. So the parameter that we are giving, the pointer, should be one that we got from mymalloc or the one that we got from myrealloc. So it should be deallocated. It just frees memory. The argument must be a pointer previously returned by mymalloc or mymalloc and not previously freed. It should not be previously freed, so we cannot call myFree for the same pointer twice, basically. You are not required to detect or handle either of these error cases. You are not required to detect or handle either of these error cases. Okay, so I don't have to write like you're not required to detect or handle either of these error cases. However, you should handle freeing a null pointer. It is defined to have no effect. Okay, you should handle freeing a null pointer. It is defined to have no effect. Got it. So I don't have to write the functionality to check whether I'm trying to free a memory that is already freed. I don't have to write it. You're not required to detect. I don't even have to detect or handle either of the error cases. That is fine. Okay. Void. Actually, from this, I have to say like I'm not sure how do we detect like if the memory was freed. Is it because like we see garbage, or do we like during freeing the memory, do we like zero it up or something? Not sure. Void star myrealloc void pointer size and the new size. This call returns a pointer to a allocated region, similarly to how my malloc behaves. These are two special cases you should be aware of. If pointer is null, the call is equivalent to my malloc size. Okay, if the pointer is null, then it is equivalent to my malloc size. Okay, if the size is equal to 0, the call is equivalent to my freeze pointer. If size is equal to 0, okay, it's just functionality that I have to like do. The first thought in my mind is to just use two if conditions to check the parameters. I'm not sure, but I guess that's the first thing that came in my mind. Uh, and I guess it's the right. If it's asking us to like use some okay, I'm just gonna figure it out later on. Otherwise, pointer must meet the same constraints as the argument to my free. Okay, so otherwise pointer must meet the same constraints as the argument to my free. What pointer must meet the same constraints as the argument to my free, as the argument is point free. Okay, got it. It must point to a previously allocated block, and it must have been previously returned by either malloc. Okay, you don't need to defend against freeze to invalid pointers. Yeah, the return value of my realloc must meet all the same constraints as the return value of my malloc. Yeah, right. Namely, it be 8-byte aligned and must point to a block of memory of at least size bytes. Sorry, of at least size bytes. So yeah, so my realloc, I think we are just like giving a new size to the already present pointer, I guess. So like, I guess that is it. So like, let's say I use my alloc uh, to allocate some size, and then I'm returned a pointer, but then later on I realize this size is not enough, so I'm going to reallocate memory. So I guess this is what this function does. There is one additional constraint on the behavior of my realloc. Any data in the old block must be copied over to the new block. Fair. If the new block is smaller, the old values are truncated. Okay. If the new block is larger, the value of the byte of at the end of the block is undefined. Okay. So if it's smaller than the initial, we'll just leave out the rest of the values. We'll just truncate it. We won't copy it to over here. And if it's bigger, we'll just copy everything. And the end of the newer block, the end parts, the tail part of the newer block must be like undefined garbage value, or we'll just zero it out. A naive implementation of my realloc might consist of nothing more than a call to my alloc, okay, a memory copy, and a call to my free. Yeah, that's fair. This is in fact how the reference implementation works. Leaving this solution in place is probably a good way to get started. Leaving this solution in place is probably a good way to get started. Okay, got it. Once you have made progress on my alloc and my free, you will want to consider ways of improving the performance of my realloc. So improving performance on my realloc, I am not sure what I should implement, but I'll figure it out. I have some things in my mind, but yeah, we'll just see. All of this behavior matches the semantics of the corresponding libc routines. Type man malloc at the shell to see additional documentation if you're curious. Okay, we'll do that. Now we are literally going to do that. I'm just going to look like what is the time past. Also, it's 24 minutes. Oh, okay, you guys can't see this. It's been like 24 minutes. Okay, 24-minute video, and I have only barely scratched the surface. I guess by making this a 1 hour video, I have a lot of time. Yeah, fair. Like today, I guess I don't have anything else to do today because I like completed my the task for the day. I've like completed like some coding questions, and I've completed learn CPP. Like I have the what I've completed. I have completed some things, revised. You can say revised some stuff from learncpp.com. Uh, so okay, I have a lot of time. So my Malak, sorry, not man Malak. Let's see. I know this is a bad idea. No, not a bad idea. I know this is a bad thing, like the spotlight search. I'll figure out the like shortcuts and all. Okay, just give me some time. Okay, so we'll go full screen. Man Malak. Let's see. This is too much of a zoom in. What? Why can't I go up? What? I can go. Okay. Okay. So, calc free malloc whatever memory allocation. Okay, I guess these are the functions that they were talking about. libc implementation of memory allocation. Okay, so void calc free malloc realloc realloc f valloc aligned alloc. Okay, malloc are and realloc functions allocate memory. Malloc, calloc, valloc, realloc, and realloc f. Allocate memory. The allocated memory is aligned such that it can be used for many data, for any data type, including LTVEC and SSE related types. The aligned alloc functions allocates memory with the requested alignment. Okay. Aligned alloc function allocates memory with the requested alignment. The free function frees allocation that we created via the preceding allocation functions. Okay. The malloc function allocates size bytes of memory and returns a pointer to the allocated memory. The calloc function contiguously allocates enough space for count objects that are size bytes of memory each and returns a pointer to the allocated memory. The allocated memory is filled with bytes of value 0. Okay. Allocates enough space for count objects. What does that mean? What is the function implementation of calloc? Where is calloc? Yeah. Size t and count. I'll look it up. I'm going into like the rabbit hole. Sorry, can anchor. Yeah. Calloc stands for contiguous allocation function. It is similar to malloc, but it initializes the allocated memory to 0. Okay. How do we call it? Phi. Okay. So if we print it, okay. So what are we doing? So we are giving it like what? Checking. Okay. So calloc we call the first is the. Where is the calloc? Yeah, the first is the count, like what count we want, and the size of. Oh, okay. I get it. So what I was reading here, so this size t, which is at least size bytes long. Okay. I'm not sure about this, but they have mentioned like size t size. It can have like two things. So by reading this, I can see like count and size. So here count, what they mean is like the number of times that we want to repeat this allocated size. Like we'll allocate, this is the unit, and we have to like allocate these many times of units of this sorry this is the unit, and we have to allocate these many times of this unit. I initially thought this is what it's supposed to be size, but I guess it's fair. We have to also tell it like what kind of data type, like should we allocate 4 bytes long, 8 bytes long, 16, 32, 64, whatever. Okay, I guess that's fair. Got it. I'm understanding everything. My brain, oof, I can feel myself getting smarter. Uh, yeah, 4 bytes long and 5 into 4, 20 bytes long. Yeah, got it. Got it. Valak. Valak function allocates size bytes of memory and returns a pointer to the allocate memory. Size bytes of memory. The allocated memory is aligned on a page boundary. Okay. I don't think I should go into like deep into this kind of stuff, but I'm going to. I guess. Okay, I guess I can find Valak on this page itself. Okay, it's not there. Yeah, let's see. What does Valak do? I get it and then it will. Yeah, I can't find Valak over here. Okay, Linux documentation. Linux.die. Hmm. 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 Okay. Valak. Hmm. Hmm. Just tell me what Valak does, bro. It's not that deep. This is the implementation of Valak, but the function possessing. Okay, the obsolete function Valak. I think we also have. Okay. The function aligned alloc is the same as memalign except for the added restriction. Okay, I'll read about this later on. Okay, the obsolete function valloc allocates size bytes and returns a pointer to the allocate memory. The memory address will be multiple of the page size. It is equivalent to. Okay, so it is like a multiple of page size. What is a page? I think I have read about pages. I think that is too deep. I think I'm entering a rabbit hole. Even this itself, like the man documentation, it's itself a rabbit hole. I shouldn't be like reading this much stuff. Aligned alloc function allocates size bytes of memory with an alignment specified by alignment and returns a pointer to the allocated memory. Okay. I guess we have to technically do aligned alloc because we have to align it based on like 8-byte alignment. Okay, so the realloc function tries to change the size of the allocation pointed to by pointer to size and returns pointer. If there is not enough room to enlarge the memory allocation pointed to by pointer, realloc creates a new allocation, copies as much of the old data pointed to by pointer as will fit to the new allocation, frees the old allocation and returns a pointer to the allocated memory. If pointer is null, realloc is identical to a call to malloc for size bytes. If size is 0 and pointer is not null, a new minimum size object is allocated. Okay, so if size is 0, okay, so if size is 0, this is what it says. If size is 0 and pointer is not null, if size is 0 and pointer is not null, a new minimum size object is allocated and the original object is freed. When extending a region allocated with calloc, realloc 3 does not guarantee that the additional memory is also 0 filled. Okay. When extending a region allocated with calloc, realloc does not guarantee that the additional memory is also 0 filled. Yeah, sure. But we have to make it sure, like we have to ensure it. No? Yeah. Realloc f function is identical to the realloc function except that it will free the past pointer when the requested memory cannot be allocated. This is a free BSD specific API designed to ease the problems with traditional coding styles for realloc causing memory leaks in libraries. The free function reallocates the memory allocation pointer to pointer. If pointer is a null pointer, no operation is preferred. Yeah, sure. The return values, it's no problem. Realloc f, I'm not sure. Realloc f function is identical to the realloc function except that it will free the past pointer when the requested memory cannot be allocated. When the requested memory cannot be reallocated. Ah, okay. It will free the past pointer. Okay, got it. So we'll just destroy that. That is a, I think that is a bad function call. Like, we'll try to reallocate memory, but if it fails, the data that is already present, instead of just throwing an error, or just, I guess even if you throw error, it will be erased. Much smarter people than me have made this function. I'm not going to criticize this because I don't know stuff about it. When I'll know about it, I'll criticize this or like praise this, whatever. Okay, so we are over here. I think I will like to. I think I'll take a break over here. I can feel my back hurting. So just a small break. It's been 36 minutes right now. I'll just pause it. Just pause it. Not bye. Pause it. Let's go. We are back. Okay. So this is where we left. So yeah, we read about this, like the function that we have to make, and about different kind of allocations that like we read the man page and all. At you guys just okay. Sorry for explaining everything. I just took a short break. Uh, my back is still hurting, but okay, we're going to continue. We are going to persevere. Checking the consistency of the heap. Dynamic memory allocators are notoriously tricky to program correctly and efficiently. One reason why they can be difficult to program correctly is because the code involves a lot of untyped pointer manipulation. Okay. Corruption introduced by mishandling pointers might not show up until several operations later, making it extremely difficult to diagnose the root cause for a crash or incorrect output. For this reason, among others, you will find it very helpful to write a heap checker that scans the heap and check it for consistency. Naturally, exactly what the heap checker can or should check for will depend on how you choose to implement your storage allocator. However, here are some examples of questions that the heap checker might ask. Is every block in the free list marked as free? Okay. Are there any contiguous free blocks that should be co-list? Okay, I will also just put this. Does it have a C? Oh, clanker. Okay. That's not a clanker. This is a clanker. Okay. To come or grow together. Oh, I guess it's like merge the free memory. Okay. Are there any contiguous free blocks that should be coalesced? Okay. Is every block okay? I'll just like explain what this means. I don't know. I'm just trying to like interpret it as best as possible. In every is every block in the free list marked as free? Okay. So I guess you know how earlier I said I asked like how does free work? Like are we setting it all to zero or are we just keeping it garbage or something? I think I know how it works. I think we are keeping a list of the free allocated memory, like earlier, which was allocated and then was freed. So I guess we are keeping a copy of it until the program ends. Not sure, but okay. This is my most. This is my best guess. Yeah. We have to check. Yeah. Every block in the free list marked as free. Okay. So every block that is present in the free list should be marked as free. Okay, that's fair. Are there any contiguous free blocks that should be coalesced? So if there are multiple free blocks, they should be merged back, and so that they are like they should be better utilized by the OS. Is every free block actually the free list? Okay. So every time we free a block of memory, we have to ensure that it goes to the free list. Do the pointers in the free list point to a valid free blocks? Do the pointers in the free list point to a valid free blocks? Okay. I have some thoughts. I have like some doubts, but I'm keeping it in mind because I don't know much of the stuff. I'll read about it. Like how does the freeing memory works? I guess this PDF should cover it. Oh, sorry, not this one. I was going to like use this one. No. Yeah, I guess this one should cover it. Yeah, Malakan free and free. Yeah, free. So how does the free work? To free or not to free? And Malakan free. Look, CA. I think it does cover how free work. Even if it doesn't, I'm not going to figure out it today. I'm just going to read this PDF. Oh no, I close the main PDF. Yeah, it's fine. No big deal. We'll go full screen again, and here we are back at it. Checking the consistency. Oh, sorry. Checking the consistency of the heap. So I think now that I am over here in this region, I should like keep it like how was it earlier? Was it full screen or not? Yeah, I think it was full screen. Okay. So we were over here. Yeah, dynamic memory allocates. I've read this. Do the pointers in the free list point to valid free blocks? Okay, fair. Do any allocated blocks overlap? Fair. Do the pointers in heap block point to valid heap addresses? Okay. Do the pointers in the heap block point to valid heap addresses? Okay. Generally, as you design the data structures, you will use as you design the data structures you will use to solve this problem, you should make a note of any relevant invariants. Your heap checker will consist of the function int check void in allocators.c. It should return a 0 if and only if your heap is consistent and return -1 otherwise. You're not limited to the listed suggestions, nor are you required to check all of them. Okay, I am going to check all of them, and yeah, as you have said, I'm not required to like I'm not limited to this. I'll think of other things too, don't worry. uh, okay, you're not limited to listed suggestions, nor are you required to check all of them. You're encouraged to print out error messages when check fails. I guess I will also print out like what error happened. You can tell the driver to check the heap after every operation by passing the -c option. Okay, you can tell the driver to check the heap after every operation by passing the -c option to the driver and looking at the checked column. You should also sprinkle heap check assertions in your code when you feel the heap might go from uncorrupted to corrupted. Example, before and after major operations on your internal data structures. I did not understand any of that part, but I'm going to read it again. I'll just look how much is it. Okay, let's no I think we I guess let's read it again. You can tell the driver what driver. You can tell the driver to check the heap after every operation by passing the -c option to the driver and looking at the checked column. You should also sprinkle heap check assertions in your code when you feel the heap might go from uncorrupted to corrupted. You should also sprinkle heap check assertions in your code when you feel the heap might go from uncorrupted to corrupted. Example, before and after major operations on your internal data structures. Okay, I'll just read it and then I'm going to Google a bunch of stuff. Remember that assertions are only checked in debug mode. Okay, remember that assertions like sprinkle heap check assertions. Remember that assertions are only checked in debug mode and are not executed in release mode. Okay, so whatever the checks that we are going to like add to like check just before and after a major like major operation on the memory, we have to like uh, add check assertions, but they will only trigger in the debug mode and not on the release mode. The heap checker is like your own internal suite of unit tests. Also, there is a suite or suite, whatever, uh, Bob suite. We will not run it against anyone else's code, and we will not look at it during cross testing or performance testing. Okay. Along the same lines, you may find it helpful to write some debugging functions that print your key data structures. Along the same lines, you may find it helpful to write some debugging functions that print your key data structures in some easy to read format on your screen. Fair. I guess I will have to like add some print statements in the debug mode. I've like read about about like adding a macro when we are debugging. I guess I will use that. I did not use that while like like just reading stuff. I was not at all like practicing, but I will do it for this one. Support routines. Let's go. Okay. So what is this? Let's go. Support routines. The code in memlib.c simulates the memory system for your dynamic memory allocator. Okay, simulates the memory system for your dynamic memory allocator. You can invoke any of the following functions in memlib.c, but you may not modify any of their implementations. Okay, memsbrk int increment. Expand the heap by incr bytes, where increment is a positive non-zero integer and returns a generic pointer. Shouldn't it be like unsigned then? Okay. Um, returns is a positive non-zero integer. Oh, it's non-zero too. And returns a generic pointer to the first byte of the newly allocated heap area. The semantics are identical to the Unix sbrk function, except that mem sbrk accepts only positive non-zero integer argument. Does sbrk also like take in negative integers, like to free up what? To reduce the heap area? As far as I'm like understanding, so memlibc has those kind of functions that involve not only about like the requested space, it is about like the entire heap. That's what I'm getting from here. So void heap lo returns a generic pointer to the first byte in the heap. Fair. Void pointer mem heap high returns a generic pointer to the last byte of the heap. Fair. Mem heap size void returns the current size of the heap in bytes. Yeah, this minus this. Or it might not be that simple, like okay. Mem page size returns the system's page size in bytes, 4 KB on Linux systems. I'm not sure what Mac OS has. Should we check? No, I don't even know what page is, so I'm not going to check. In the code you write, you may not invoke any of the functions in memlib. Okay, in the code you write, you may not invoke any of the functions in memlib.c that are not listed above. Okay. Any of the functions in memlib.c that are not listed above. Fair. Additionally, you may not invoke any of the wrappers to this function in myallocator wrappers.c. Okay. These functions are not for use by the TAs who are grading your submissions. Okay. So I have to write these functions, and these are for heap. So I'm not sure, like I have some doubts. Okay, let's read it. I have some doubts, but I will clear them like later on. I understood all of this stuff, but I have like some doubts related, like what these functions are actually doing, like what are they doing? Are we only supposed to use these functions? Like this point, this is like nothing. So like expands the heap by increment bytes. So like, are they talking about like this is like the basic like memory allocation? Yeah, nothing mentioned over here. I think they are talking about like the general heap, the bigger heap, and like these are the functions that we want for the individual process, and these functions are like for the heap, the big heap, the big G. Okay, so yeah, let's keep reading. Also, okay. Additionally, you may not invoke any of the wrappers to these functions in myallocator wrappers.c. These functions are for use by the TAs who are grading your submission. These functions are okay. In the code you write, you may not invoke any of the functions in memlib.c. They are not listed. They are not listed above. You may not invoke any of the wrappers. Okay, these functions are for use by the TAs. TAs. Not sure what TAs are. Test, assign, assessment, what? Who are grading your submissions. Okay. Writing external validator. For the cross-testing component of this project, you will be writing a black box external validator that can test any malloc implementation. Your validator will be used to test your peers' implementations. Okay. It doesn't matter. Okay, look in validator.h for the skeleton of your validator, which lists all of the invariants you want to check. These are reproduced here for reference. For the given traces, neither my malloc nor my realloc should return null. Okay. Allocated ranges returned by the allocator must be aligned to 8 bytes. Allocated ranges returned by the allocator must be within the heap. Allocated ranges returned by the allocator must not overlap. When calling my realloc on an existing allocation, the original data must be intact up to the reallocated size. We have provided a linked list representation for the ranges, but you must provide the add and remove operation for this data structure. What does that mean? Sorry. Okay, so whatever we have to whatever external validator, which is black box that we write, it will be tested against our peers. This our peers project. Test your peers implementation. Look in validator for the skeleton of your validator, which lists all the above invariants you want to. Okay, these are the invariants. These are the basic invariants that we found like validating the function. We have provided a linked list representative for the ranges, but you must provide the add and remove operations for this data structure. What is add and remove? Is it like the code is ready and we have to like add instructions or something? Not sure. Okay, so the trace based driver, I guess this was the driver. The driver program mdriver.c tests your allocator.c package for correctness, space utilization, and throughput. The driver program is controlled by a trace file. Each trace file contains a sequence of allocate, reallocate, and free commands that instruct the driver to call your my malloc, my realloc, and my free routines in some sequence. Okay, it also contains write commands that instruct the driver to read and write the allocated memory. It also contains write commands that instruct the driver to read and write the allocated memory. Run mdriver locally on your VM as opposed to AWS run. The driver mdriver accepts the following command line arguments: -t trace dir, look at the default trace files in directory instead of the default directory dot traces. Okay. F trace file, use one particular trace file for testing instead of the default set of trace files. -h print a summary of the command line arguments. -b verbose output, print a performance breakdown for each trace file in a compact table. dash capital V. More verbose output prints additional diagnostic information as each trace file is processed. Useful during debugging for determining which trace file is causing your mymalloc package to fail. Dash C, check the heap after every operation. Yeah, this is the dash C that we are talking about. Dash C using your check function. Fair. The simple implementation given to you will run out the memory on the realloc trace and throw an error. The simple implementation will will run out of memory. Given to you will run out of memory on the realloc trace and throw an error since it does not utilize freed space appropriately. Your implementation will be expected to pass all the trace files in the traces directory. Okay, okay, got it. So the test like the traces that the the company named Snail Speed or something, whatever the traces are, it is present in the directory and it should like work like this. Uh, the traces that we will test your implementation with traces other than those provided in the traces directory. Okay. More information on the format of the trace files can be found in the README included at the top level of the project 3 code repository. Oh, is it? Is there a README? Okay, I'll look at it. Uh, I think I will forget that easily. Let's look at it. No, can't find the. Not able to find the README that they were mentioning. Okay, it's fine. Let's go for auto tuning. So optimization and implementation strategies in a program can affect performance considerably. A tuning framework searches through different strategies and find the best programming implementations. If you would like, you can use the OpenTuner auto-tuning framework to tune parameters of your allocator's execution. Okay, you can use the OpenTuner auto-tuning framework to tune parameters of your allocator's execution. This is not required for you to receive full credit. Yeah, okay. To tune your program, you first need to express the optimizations in your program as parameters and define a search space of possible values. To tune your program, you first need to express the optimizations in your program as parameters and define a search space of possible values. The job of the auto tuner is to automatically traverse the space searching for the most effective combination of parameters. OpenTuner is an open source framework developed at MIT, which we recommend for this project. To run OpenTuner, go to the project directory and follow the steps in the README file. Also revisit homework 6 for some instructions on running OpenTuner. Be careful, auto-tuners are designed to find the most optimal configuration for whatever test cases you run them on, sometimes in ways that a human coder would never consider. If your tests are not general enough, you can overfit your allocator to the auto-tuning inputs. This can cause your code to run slower on somewhat different test suites that you will actually be used for grading. More information about auto-tuner. Okay, I guess this is the auto-tuner. Yeah, this is the clickable link. So what I understand from this, open auto-tuner open tuner like identifies like what is the better implementation, like it benchmarks something. Like I'll just read it quickly. If you to your tuner program, you first need to express the optimizations in the program as parameters and define a search space for possible values. Okay, I don't understand this. I go. Okay, I'm just keeping this aside for a minute because it's like too much confusion in my brain, and it's going to increase. Oof. I think I need to take a break. I've been sitting in the same place for like about an hour now, and I think I need to take a break. Real program performance testing. Uh, how much is the PDF remaining? Oh, it's a lot. This is the main part. Okay, we will read this later on. I'll just take another break and I'll be back at it again. Hey there. Hey there, I'm back. So let's read again. So let's read auto tuning again. So let's go. Optimization and implementation strategies in a program can affect performance considerably. A tuning framework searches through different strategies and finds the best performing implementations. Uh, okay, is it working? Yeah. I just wanted to check if it's working. So it finds the best programming implementations to different strategies. A tuning framework searches through different strategies and finds the best programming implementation. Okay. If you would like, you can use the Open Tuner auto tuning framework to tune parameters of your allocator's execution. Okay. Tune parameters of your allocator's execution. Okay. This is not required for you to receive full credit. To tune your program, you need to express the optimizations in your program as parameters. Okay, a search space of possible values. The job of the auto tuner is to automatically traverse the space. Hmm. Search for the most effective combination of parameters. I'm not sure what parameters in this case are. It's saying like the optimizations that I've made. You need to express the optimizations in a program as parameters. Not sure what it means. Open source developed by MIT, which we recommend for this project. To run Open Tuner, go to project directory and follow the steps in the README file. Okay, I'll read this. Okay. Be careful. Auto tuners are designed to find the most optimal auto configuration for whatever test you run them on. Sometimes in ways that a human coder would never consider. Sorry. If your tests are not general enough, you can overfit your allocator to the auto tuning inputs. This may cause your code to run slow on the somewhat different test suite that will actually be used for grading. For information about auto tuner can be found in the conference paper Open Tuner. Let's read this. Copy link and the official online tutorial. Let's just look at the GitHub for now. I thought this was the GitHub link. I am not sure about any of this. Just a minute. Back at it again. So the official online tutorial. Okay, yeah, this is what I was looking at. Program auto tuning has been shown to achieve better or more portable performance in a number of domains. However, auto tuners. Let's just search what is auto tuning in CS. Auto tuning and overview. Let's see. Okay. Cookie settings. Performance cookies are off. Confirm measures. Okay. Auto tuning is an automated process in which software systems optimize their own internal parameters to suit particular execution environments, such as identifying compiler optimizations that maximize software performance on a given architecture. The primary goal of auto tuning is to derive an efficient configuration by defining appropriate software knobs, resulting in implementation that satisfy specific metrics, including energy consumption or execution time, because manual search of design spaces is often infeasible due to the size and complexity. Automated approaches are required. Okay, got it. So I guess it will be optimizing like the assembly code or something, whatever. Real program performance testing. In addition to the traces, we may also test your allocators on real programs to determine the performance on realistic workloads. We have provided a simple performance test for your allocator in allocator test.c, which can be run by executing the file allocator test. For the beta, we will not be grading your performance against these additional programs. However, We do recommend you play around with this to get a feel for the performance of your allocator, since we may test your allocator against other real workloads for the final project submission. Okay, so rules and reminders. You should not change any of the sources in the distribution except for the allocator.c, validator.h, and opentuner parameters .py, parameters.py files. You are free to add new files and update the make file appropriately if you wish. You are free to add new files and update the make file appropriately if you wish. All the other files will be overwritten with fresh copies during cross testing. Okay. You should not invoke any memory management related library calls or system calls. Do not use okay. You should not invoke any memory management related library calls or system calls. Do not use malloc, calloc, free, realloc, sbrk, brk, or any variants of these calls in your code. Okay, so I'm not even supposed to use sbrk or brk. What am I supposed to use then? Okay, you should not use any parallelization for this project. This project is meant to be single core only. Okay, the total size of all defined global and static scalar variables and compound data structures must not exceed 512 bytes. The size of all defined global and static scalar variable and compound data structures must not exceed 512 bytes. Okay, 512 bytes. Okay, got it. Okay, so all data structures that allocate memory on heap, must use our allocator heap interface. Okay, so I cannot use. Okay, got it. All heap memory space used by your data structures will be counted under space utilization. Got it. Evaluation. Please remember to add. Okay, let's first discuss what this means. So first of all, the first point, you should not change any of the sources in the distribution except for the allocator.c. Allocator.c is our functions. So these functions are inside allocator.c. Oh no, this is are declared for functions which are declared in the allocator interface.h and defined in allocator.c. Yeah. So these are the 4 functions that are defined in allocator.c, and we can change those. We can also change validator.h, which is this one. Where was it? Oh, it was somewhere. Where is the validator? Oh yeah, writing an external validator. Full screen. Yeah. Writing an external validator. Where was it? Oh, I lost it again. Yeah. Okay, here. So yeah, this was it. When we are writing our external validator, to like ensure it's working, and also cross test it maybe. Okay. And open tuner parameters.py. Okay, we can add as many files as we want, only for the like coding purposes, and all the other files will be overwritten with fresh copies during cross testing. Yeah, sure. You should not invoke any memory management related library calls or system calls. Okay, I had the idea that we will be using like we won't be using malloc, calloc, free, realloc, okay, but we'll be using sbrk, brk, or something, or any variants of these calls. I'm not sure what we are going to do right now. Like I'm not sure how are we supposed to like use. Is it like they are going to provide the functions by themselves and we have to just like organize stuff and all? Like what? Okay, I'll figure it out. You should not use any parallelization. Okay, yeah, sure. We have to make a single core only. The total size of all defined global and static variables and compound data must not exceed 512 bytes. Yeah, whatever variables we declare, we have to use like our allocator heap interface itself, and also whatever data structures we use is considered under space utilization of the entire project. Okay, let's see for evaluation. Please remember to add all new files to your repository explicitly before committing and pushing your final changes. Okay, please remember to add all new files to the repository explicitly before committing and pushing your file changes. Your grade will be based on the following: performance of correct code. Two performance metrics will be used to evaluate your solution. This is a little bit different from what we have done in previous projects. Space utilization, the peak ratio between aggregate amount of currently allocated memory that is allocated via mymalloc or myrealloc and not yet freed via myfree, and the size of the heap used by your allocator. The optimal ratio is of course 1. Yeah, definitely. You should find good policies to minimize fragmentation in order to make this ratio as high as possible. You should find good policies to minimize fragmentation. Yeah, got it. The space utilization U would be calculated as maximum of M and or 40 KB divided by maximum of H 40 KB. Maximum of M, I guess, is memory. Uh, Comma 40 KB, I guess it's maximum. What maximum it can be 40 KB. So my maximum heap is of size 40 KB. Okay, got it. Throughput, the average number of operations completed per second. The driver program summarizes the performance of your allocator by computing a performance index P, which is a weighted geometric mean of the space utilization and throughput. P is exponential of W. What is W? W log U, which is this space utilization, whatever this formula is. Okay, minimum of 1 T divided by T libc. Oh, T libc must be okay. I guess I'll see what it means now. Where U is the space utilization, T is the throughput, and T libc is the estimated throughput of libc's malloc on your system on the default basis. Since both memory and CPU cycles are expensive system resources, we adopt this formula to encourage balance optimization of as expensive system resources. We adopt this formula to encourage balance optimization of both memory utilization and throughput. Ideally, the peak performance index will reach P is equal to exponential W log 1 plus 1 minus W log 1 is equal to 1 or 100%. Specifically, we have to set the value of W to 0.5. So performance in terms of memory utilization and throughput are equally important. To receive a good score, you must therefore perform well in both categories. Okay, got it. What is W? Not sure. You will receive credit for each trace that your allocator successfully handles as evaluated by a validator. We will test your implementation with traces other than those provided to you with the code. As mentioned previously, we may also test the performance, both throughput and utilization of your allocator against other real programs. Note that we will not be doing this for beta submission. We have provided a simple allocator test that uses your allocator, which you can modify to test against other programs. Okay. Progress reports. You must individually submit a personal progress report every Thursday that briefly describes the project you performed during the past week. The report should be short, typically a paragraph in length, describing what project work you engaged in and about how much time you spent on various activities. Additionally, if necessary, describe any issues that may have arisen, such as with teammates or rather especially with the teammates. Okay, I don't think it was necessary. Directory LOC memory summary. Along with your past page description, include a summary of your daily number of lines of code you committed using the following script. Okay. Addressing mid pose comments. The mid pose will give you feedback on your code quality. We expect you to respond MIT. Oh, it should be MIT whatever. Final submission. We will review the MIT pose comments and your write-up to ensure that you are addressing them. Test coverage. Your myalloc validator should catch all violations of the invariants we listed. We will run it on every other teammate's mymalloc implementation and compare your results with your own to determine your grade. Beta and final group write-up. We are required to submit on LMOD a group write-up for both the beta. Important, I guess it's like the coursework specific to materials present in your code and write-up. As always, diagrams may be useful. Okay, I think it's like project specific, so I don't think I need to read all of this. Hints and tips, yeah, definitely I will read this. Okay. Spend plenty of time writing your internal consistency checker and other debugging tools. Okay, spend plenty of time writing your internal consistency checker and other debugging tools. This will save you time in the long term, definitely. Use the mdriver-f option. During the initial development, using tiny trace files will simply debug. Okay, using mdriver-f, use mdriver-f option. The C option that we looked, I guess the F option. Okay, during the initial development, using tiny trace files. During initial development, using tiny trace files will simplify debugging and testing. We have included two such trace files. Use the mdriver-v and capital V options. The -v option will give you detailed summary for each trace file, and capital V, which is verbose, will also indicate when each trace file is read, which will help you isolate errors. Use a debugger such as GDB. I think I should learn GDB. A debugger will help you isolate and identify out of bounds memory references. Use assertions. When debugging a failure or a crash, sprinkle assertions in your code before and around the crash and rebuild it in debug mode. When your program crashes during an assertion failure, it prints out field condition and the line number of the failed assertion, which is more helpful than segmentation form. Yeah. You may want to explore encapsulating your pointer arithmetic in static inline functions. You may want to explore encapsulating your pointer arithmetic in static inline function. We may want to encapsulate pointer arithmetic in static inline functions. Pointer arithmetic is in memory managers is confusing and error prone because of all the casting which is necessary. You can reduce this complexity significantly by writing helper functions or macros, if appropriate, for your pointer arithmetic operations. Do your implementation in stages. We recommend that you start by getting your mymalloc and myfree routines working correctly and efficiently and test it on the traces. The realloc trace should be tested after the implementation of myrealloc. Remember that the reference implementation of myrealloc is built on top of myalloc and myfree. Yeah. Use a profiler like perf and gprof to identify hot spots. Remember that all of these techniques we have discussed so far. Yes. Start very early. It is possible to write an efficient malloc package with a few pages of code. However, we can guarantee that it will be some of the most difficult and sophisticated code you have written so far, and probably also the most difficult to debug. If you wait until the last minute, you may find that you do not have enough time to produce a worthwhile product. Good luck. Okay. MIT OpenCourseWare. Oh, so this is what OCW means. Performance engineering and performance system. Performance engineering and software systems. For information about citing the material and use terms. Should I open this? Oh, just okay. Let's copy this. Okay. I should search this. Search. Yeah, this is it. Okay. Charles Laserson, Julian Shun. Okay, so projects. Yep, this is the project. This is the one. Okay, this is the third one. Bit hacks, collision detection, laser chess. Okay, whatever. Okay, cool. Where can I find, like, okay. This is like the zip file. Okay, let's download the zip file. I'll look at like what all stuff is in there. I'm not sure why I'm using Safari, but it's the default one. Also, it's like efficient and fast. Clin.py, mymalloc. Oh, okay. So this is the code. Uh, what did I wanted to see? Yeah, allocator.c. Oh, why did I double click it? No, 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 no. Don't open the text code. Oh, it's going to open the text code. Okay. MIT. Okay. Let's look at the code. So cd downloads. Oh, I shouldn't be showing this. cd download MIT. Okay, now I can move freely. No. This is what they were talking about. This is the README. That's a lot of stuff. This is about you autotuner, trace files, M driver. Okay, let's look at the code itself. The main program able to run your allocator on one or more traces is M driver, memory driver. What is clin.py? Not sure. Not going to look at it. Oh no, what did I press? Oh no. Please tell me that was not permanent. I'm not okay. Let's go. Okay, so sorry. What was I going to take a look at? Allocator.c. Yeah. My check. Where is the init function? Yeah. So this is the init function. I have to like use. This is the alloc. My free. Sorry. Oh. Okay. Wait. Was there a working version of that? It shouldn't be, right? Oh, okay. So this is use my malloc. Okay, okay, got it. Okay. Mem is brk. My free, it's not doing anything. My realloc isn't doing anything also. It's calling my malloc. Okay, my malloc is the main one. So malloc, allocate a block of incrementing the brk pointer. Allocate a block by incrementing the brk pointer. Always allocate a block whose size is a multiple of alignment. Okay. We allocate a little bit of extra memory so that we can store the size of the block we have allocated. Sorry, take a look at realloc to see one example of a place where this can come in handy. Sorry, expands the heap by given number of bytes and returns a pointer to the newly allocated area. So void p mem is brk. I have to take a look at what mem is brk is. Okay. So if p is void -1, if pointer -1, oops, an error of some occurred. Okay. So void pointer 0 -1 what? Okay, else. Okay, then we return a pointer to the rest of the block of the memory. Sure. Let's take a look at mem as brk. So rg, I just go inside this. Yeah, rg mem. Now it's visible. Ls mem is brk. So it's in mem libc allocator.c bad allocator. So this is the one. Primary, okay. Heap low, mem star, the heap high, mem brk -1, okay. It's just incrementing the size of the stuff. Simple model of the SBRK function extends the heap by increment bytes and returns the start address of the new area. In this model, the heap cannot be shrunk. Okay, got it. So I'll be figuring out what the code is later on. As I've said, I'll be like reading this stuff first, and then I will jump on to their implementation, like what they are doing, what is it, what am I supposed to do, and all that. I'll also read some of this, like lecture videos, if it is possible. Oh, this is a bit hacks, C2 assembly, races, analysis, multi-thread, timing, storage allocation. I guess, yeah, this one. I guess I'll watch entirety of this. Is there a where is the YouTube? There should be a YouTube playlist for this, right? Lecture videos. What is download course main? Or this must be downloading every single stuff. Let's try this. So these are 1 hour courses, and okay. I think it will be really helpful if I watch these, but okay. So this is it for okay, I'll just keep this as the background. So this is it for this video. Thanks for watching, and I guess yeah, it's all about figuring out. I am a total noob in this. I don't know much of the stuff. As I've said, I haven't if I can just say that I haven't used malloc. Okay, 1 or 2 or 3 times doesn't count. You can just say I haven't used malloc. And so I will be figuring out stuff. I'm just learning, exploring, not using no clankers in this stuff. And yeah, I'm not sure who is going to watch this, but if you're thanks for watching, man. Thanks. And thank you. Bye. I'm Aditya Pacharne, and I'm an engineer for fun.